All right. Well, we're halfway through week 4, as you know, and so what we have done, what we've talked about so far, is we started talking about fluid properties. We talked about viscosity and surface tension and unit weight. Of those, we used unit weight and density to be able to define some expressions that define fluid pressures at a point. We use those expressions to be able to not only find fluid pressures at a point, but to be able to go up and down and across in the fluid, which is part of, I guess, defining fluid pressures at a point, and integrated those to be able to define behavior of fluid pressures on structures. I'm not sure whether this will play or not, but this is a time lapse. I saw it on the TV, but I didn't see it on here, so let's see if it does play or not. But of course, the things that we've done so far up to this point in terms of buoyancy and fluid pressures acting on and in structures, if you like, the weights of fluids in structures, are actually all you'd need to be able to understand exactly what's going on and to design actually what's gone on with the Costa Concordia, this ill-fated cruise ship on the Mediterranean coast of Italy, on the west coast of Italy. And I don't know how long this runs, so I guess it's not too long. And so the solution was, obviously, it's almost capsized, but it was stopped by the fact that it was on a ledge that slopes down to your right. And they attached these big, heavy containers on the port side, I guess, of the ship. And what they did was they built, I don't know if it's underneath here, they built a ledge underneath it, so as they rotated it around, it wouldn't slip down this the side of this hill. And so there's a ledge that it could rest on, because I presume it's not particularly buoyant right now, because it's full of water, because all the compartments, watertight compartments, are not watertight anymore, they're filled with water. And what they did, maybe there's the figure below that we looked at the other day is there to kind of illustrate this in more detail. Yeah, it is. Okay, so that's exactly what they did. So they attached these canisters here. They filled them with water, I think, to make them heavy. So you could look at the moment arm that these would put around some center of rotation of this. And so the center of rotation would be where this would physically rotate around. I guess it would be this point here. You fill these up so they're heavy. You pull on this to be able to pull it down. And so it takes up this position. You weld, which they will now do, weld some containers on the other side. They'd have to submerge these containers and fill them with water first if they're going to get them to be at the right elevation on here so they can attach them. And then they blow out the air from the water from here by blowing in air, and all of a sudden you change the buoyancy, and you could do all those calculations. You're not going to have to do those calculations. I'm not suggesting that as a prelude to anything, but you could do all those calculations based on what we know about fluid pressures working on structures, right? So that's the reason that some of these bulkheads, the walls that compartmentalize the hull so that if you get a puncture in one part, it doesn't, the effects of it aren't felt throughout the whole ship because it's isolated just in that one length. The pressures on those will cause them to fail, maybe, and don't know whether they failed or not. You know that when it's sitting here and it's filled with water, we know that the fluid pressures acting on it are controlled by the pressure distribution of this incompressible fluid. We know how to calculate that. We know how the center of gravity here would provide a moment about this point, and so if we were calculating this and pulling on this, then the force that you have to apply here you could calculate by knowing what the physical weight of this ship is, what the extra weight of this container is, and just by taking moments about the rotation point, you'd be able to figure out exactly what's happening. I suppose you'd also have to take in the fluid pressures that are acting on this side and this side, but you know how to do that. So everything that we've done so far, I don't think you need any more technology or science or engineering to be able to do the calculations than you have in your arsenal right now. So it's kind of interesting that you could solve a problem that's relatively not a simple problem, and you can do that, I think, after just a few weeks. So that's one topical thing in the news right now. We talked about fluid statics. We also talked about accelerating fluids for static fluids, and that's kind of where we'll move from further from now. And we talked about both accelerating fluids in linear acceleration, but also accelerating fluids in rotational acceleration. And it's not completely esoteric why we might do that, because this is the principle by which a centrifugal pump works, right? So you have a disc that rotates. The disc has some flukes, some paddles on it, if you like. That disc spins very quickly. The water that's sitting between those paddles gets spun around and flung out laterally. As it gets flung out laterally, it finds its way into an external pipe. And so this is basically the principle of a centrifugal pump. Exactly the same principles of taking a fluid in a can and whirling it around your head on a string. Is the water wants to physically be thrown out. Once it's thrown out, it goes up this pipe. And just by merely turning this, the paddles on this wheel, you're able to pump water. So that's so it's not without reason that we're talking about rotational accelerations as well. So those, if you like, were our first forays into this, and they were all really looking at fluid pressures in static fluids. And so now what we want to do is we want to make the next step, and now we want to look a little bit at fluid pressures in moving fluids. And so it's not really very different. I'm not sure what we're going to see at any particular pace in here. I mean, there's some obvious cases where moving fluids have an impact. So if you look at, for instance, the powering of a yacht, if you look at the wind acting on the sail, if there's no wind, the pressure on one side of the sail versus the other side of the sail is the same, and there's no net motion if you're sailing downwind, for instance. And only if you have a different pressure between the upstream and the downstream will you actually get some motion attached to it. So intrinsically, we're looking at motion of fluids applied on a sail, which is really, in some sense, an airfoil. And actually, you can see it here, and actually you could see it there, is that these sails actually do look like airfoils in this particular case. I guess we've already missed it. And that they have, instead of just being the thickness of the cloth that you have in them, they actually have two layers, and they're held apart by some ribs, which actually make them much more the shape of a wing, not just the curvature of the wing, but actually the thickness and the shape of an airfoil as well. These are catamarans. They also have hydrofoils attached to them, so you sometimes see them raise out of the water. I don't know where exactly in this movie that might be if they're rolling. But if they're going fast enough, then they have legs underneath them that have airfoils on them. If they're going fast enough, then the lift on the reduction in pressure on the top side of that airfoil versus the bottom is what allows it to lift. It's the principle by which we fly airplanes also, right? The Venturi effect, or also the Coanda effect. But are they up there on their airfoils? Can't tell. Looks like they are, actually. No, maybe not. And of course, the United States aren't doing very well right now against New Zealand, who were, I think, 6-1, and it's best of 17. So I guess it's the first to 9, is it? And so to understand something about the processes that control this, among others, we need to understand something about moving fluids. Okay, so that's enough for that. What else do we have? Okay. So other moving fluids, I'm going to get rid of some of these. Don't want Costa Concordia anymore. Is this going to run? So the other graphic illustration of fluid pressures from moving fluids from stagnation, of course, is what not to do at an airport. This is staged, of course.
Engine runs are loud and dangerous.
The sound. Well, we can leave the sound.
Jet blast is powerful.
So, I'm sure you've all seen that. Looks like to me that that's almost certainly San Francisco Airport. I'm pretty sure. So it's all staged, of course. I think there probably wasn't anyone driving that at the time. But this is it's selected to be. Oh yes, it's being towed. You can see, right? So it's just blown across it. So a lot of force that comes out of an engine for a plane, and perhaps not surprising, right? You're lifting quite a heavy weight, and you're moving quite a heavy weight down the runway to get it going in the first place. And so that's a case where we have disequilibrium fluid pressures, if you like, on the front of it relative to the back, merely by the fact that actually, what are we doing? I mean, we're dealing, all of the equations that we said we dealt with before were due to F equals ma, and that was the single expression that we really used to derive the expressions that we've used already. So actually looking at, for instance, the thing that pushes this car off the runway is, if you like, throwing this as air or a liquid at the car. If you throw this at a car window, it bounces off, it applies a force to the car. If you throw a big one, of course, it would move the car over. But airflow is really just a whole series of these coming one after the other in a line, like kicking them out, for instance, out of a fire hose or out of a Nerf gun type thing. So it's nothing more complicated than that we're dealing with in this particular case. And so it stands to reason then that the rationale that we can use is we should be able to use the expressions that we've developed already, which rely on F equals ma, to be able to define the behavior that results from moving fluid. And so that's what we'll attempt to do today. And so we've kind of jumped in there already because we've talked about some of these things. If you remember, the very first time we met, we talked about Bernoulli's equation. In fact, we used it to illustrate the point that if you write Bernoulli's equation in terms of lengths, which is one way that you can write it, then we could divide some of the terms relative to each other, and because you're dividing a term of length by another term of length, those terms should actually be dimensionless. And so we use that in our exploration, if you like, of dimensionless units or dimensions and units to be used in fluid mechanics, maybe the first or second time we met, I think. And so now we can go back and try and figure out exactly how we might recover the Bernoulli equation, which is really actually it's the centerpiece, if you like, of this class. And so the basic idea that now, instead of looking at fluids which are static, now we're looking at fluids which actually travel along a flow path. So before, we used to have a little differential cube, which is our ball of fluid that happens to be in our system, but now it's moving along some flow path, which we like to be able to figure out exactly how we define that behavior. What are the forces that we have to apply to it to get it moving? What are the forces that are applied if it hits something and stagnates, just like in the case of the truck on the runway that we just saw? And again, it comes down back basically to this idea of, we can use again one of the expressions we developed, actually the major expression we developed, which relies on Newton's second law. And so the idea is that we can define behavior along a streamline. And so if you know the path that a particle of fluid will take, then our hope is that we can write this equation, this relationship, at a number of these different points. And so long as they're on this continuous flow path that the fluid particles will take, we can equate it to something, and therefore we can use that to calculate one unknown variable that we don't know along that pathway. And so there are some requirements of that, and so we'll briefly talk about what those requirements are, and we'll come back to it. And they're these four. So it only applies so long as these assumptions are in case. So it won't matter so much for you to worry about those things in solving these expressions, but it's useful to know what it can and can't apply to. It can't apply to compressible fluids. Fluids have to be incompressible. And so that's sometimes a little misleading. We know that liquids are typically incompressible because they don't compress very much by definition. And gases, as in the air that we're sitting in, are typically somewhat compressible. But that's not the whole thing, because we could actually use Bernoulli to solve the problem of the air hitting that truck at San Francisco International. And really what the issue is in addition, rather than being incompressible, no large, whoops, didn't need delta, small pressure changes. In gases. So I guess that's really the issue. So if you know that if you have a small pressure change in a gas, then you don't change its volume very much, because even though it's compressible, you're not applying a very big pressure change to it. So we can apply it to gases and airs, and we will apply it to gases, which are, of course, quite compressible. But the issue there is that we're interested in the fact that we have small pressure changes. So that's one thing to keep in mind. Irrotational just means that there are no eddies in the system. And so when we have circulations downstreams of weirs, for instance, where you have circulation occurring in eddies, both in vertical plan or in circulatory in plan view, as you look at a river, then that's not applicable for us, so we don't have to worry too much. Steady means that is important. So the most important ones, because they occur, are that the fluid pressure changes shouldn't be large. Don't worry about these because we won't have to deal with those so much. Steady behavior means that it's not changing in time. And so in other words, if you look sideways at a river which has a weir in it, and you look at the velocity that you have at this particular point on the streamline at point 1, and you look at the velocity that you have at this point on the streamline at point 2, if you look now, it has the same velocities as it does in 10 minutes time, in an hour's time, in 2 days' time. So it means that this velocity field really isn't changing in time, but it is changing in space, right? The velocity here isn't necessarily the same as the velocity here or here or here or here. So it can change in space, but if you're looking at it in a static reference frame, then the velocities everywhere will be the same, the pressures will be everywhere the same, and the elevation of this free surface will be everywhere the same in time at a given point, right? So that's what we mean by steady. And perhaps the other most important thing is that it's inviscid. There is no viscosity. So in other words, the viscosity is low, or we assume that it's 0. And we can actually get around that later on, as we'll talk about when we deal with the energy equation. But what that physically means is that there's no energy loss within the system. And so if you think about energy losses in fluids, it's no different than energy loss in statics case. If I drag this bag across the table, it's using up energy. I have to apply energy to pull it. It has some weight, and I'm applying a force to pull it. And it's expending that energy in friction on the base, which is expending in heat. And so fluids occur in the same way as if you push fluids downstream, or you push fluids, more importantly, through porous media, which many of you are involved in, environmental systems engineers and petroleum engineers and mining engineers for that matter. If you look at pushing it through porous media, as you go from upstream down towards someone's well downstream, then pushing it from the pressure upstream to the pressure downstream, there's a difference in pressure which is eaten up by the fact that this has to flow through the porous medium to get there. And the viscosity in flowing through the porous medium takes energy out of the system because it dissipates it as friction against the walls of pores. And that is basically what you make up for in permeability, for instance, if you deal with those systems. So anyway, so if we're dealing with Bernoulli, these are the 4 main issues. It has to be inviscid, the system has to be steady, and it's typically small pressure changes in compressible fluids or incompressible fluids. And so those are the conditions that we'll deal with. Our interest is in dealing with a frame of reference, which is along a streamline. And what we can look at, well, I'm not going to use these notes. So I'm going to diverge from these notes. I'm going to start writing some things, which is what we've been wont to do in the past. And so we'll kind of make the case of where we're going in this from these notes. Okay? Everyone okay? So we are what? So this is our first foray into fluid dynamics. A moving fluid. And so we're ultimately going to develop the Bernoulli equation. That's where we want to get. After Daniel Bernoulli, right? He's a scientist from the late 1700s. And so this is the basic idea is this. So if we have an airfoil that's sitting in a flow field, then we could imagine that the fluid that flows around that can flow on a variety of different trajectories, both above and below it. I guess we can draw that as a split flow line, or we could do it as two separate flow lines. And so we could imagine behavior in two different modes. And the two different modes that we have are one which is along the streamline, which is where we can write Bernoulli at a variety of different places along here. But we can also write it normal to the streamline. And so where this angle here is a right angle. And so what we'd like to be able to do is be able to come up with some kind of relationship which defines these behaviors, both as we go along a streamline from upstream to downstream. And if we wanted to be able to go across the streamline, to be able to see, for instance, how fluid pressures might change with space, how velocities might change with space, and how elevations would change with space, which is, of course, given because we know exactly what all the elevations are in this particular case. And so what we want to do is to be able to figure out exactly what the behavior might be along that pathway. And so we've dealt with that in some respects, right? If you remember what we dealt with when we talked about our little accelerating fluids, if you recall, we had, for instance, we dealt with behavior so that we had in our coordinate system, which is right-handed, with z upwards. So remember that we have z defined upwards. We could write an expression which allowed us, for instance, to be able to look at the fluid pressure we applied on the base, the fluid pressure that we applied on the top. We could apply an acceleration to that in the z direction, which is positive in the direction of the axis. And it also had some weight attached to it, right? Which was equal to just the volume multiplied by the unit weight of the fluid. So that was our attempt to be able to look at our container, which we put in the elevator. We accelerated upwards, we accelerated downwards, coming up and down. And from that, we could say something about how fluid pressures would change within a container. So what we could do is we could take that and resurrect that expression, if you like, to be able to basically look at, for instance, passing a fluid in the z direction, and look at that little box, if you like. Take that little box at position 1 and move it along the streamline to position 2. Right? So we're going to take our container and we're going to move it from 1 to 2 using the expressions that we had before. And I won't rederive those expressions, but you remember that our static expressions were this, right? It was something like, I'll write these as well, they're partials or full derivatives, it doesn't really matter. Minus dp dz minus density times elevation. Density times gravity minus acceleration, just do it in order, right? Density times acceleration in the z direction, and that was equal to 0, right? So that was the expression we had. And so what we could do with this is we could assume that we could write this along this line here. If something's going in the vertical direction, then that is also a streamline, right? If you imagine a fluid going vertically. So if we take this along streamline idea and make it this, then we can maybe do something with expression to be able to figure out exactly what the behavior along that streamline would be. The other thing you might recall is that this expression, if we go back to it, this part was equal to F, and this part was equal, and this part was equal to mass times acceleration, right? So this is just Newton's law written in a different way. And so what we might want to do is to write this in some way. So what can we do? Why don't we write the acceleration in the z direction in some particular way? So what is acceleration in z? Bless you. Okay? By definition, acceleration is this, right? Change in velocity with time. If we wanted to, we could also write this, of course this is velocity in the z direction, but let's not worry about that. We could also write this as this. And we could also multiply it by 1. Right? dz over dz is just equal to 1. And so what is this? This, by definition, the change in location with time is a velocity. So this is equal to change in velocity with location. Don't confuse my z's and t's. Z, z, t, etc. And this, of course, is a velocity. And this we can write, if we wanted to, as a half change with elevation of v squared, right? And so we can check that if you like. Let's just provide a little check of this. And so what's this? This is, if we take this expression that we have here, just to check, change of v squared with elevation, we can write that as equal to a half dv all squared dz, and again we can multiply by 1, and if we take that and do the derivatives of this, this is v squared. If you take the derivative of v squared with respect to v, you get 2v divided by a half, which is v, which is just v dv dz. So all I'm trying to make sure you understand is that this expression can always be written as this. It's a standard result, right? And so what we can do with this is that now we have this expression here. This is actually the acceleration that we have here. So what we can do is we can come back to this expression here, and we can write out minus change in pressure with location, minus density times gravity, minus density of the fluid times a half rate of change with location of the velocity squared. Right? So we've done nothing other than just figure out exactly what acceleration is and be able to substitute it into this. And that's the differential form of this expression. We could multiply everything by dz. Still equal to 0. We could, in which case we lose this and we lose this, and we lose this and we lose this. And we could integrate it, so I'll just write it out. So minus integral of change in pressure minus density times gravity times the integral of elevation minus a half rho v squared, I guess dv squared, which we integrate as well. And if we write that out in, you could do this integral between the limits, or you can do it just with a constant as we did before. If we integrate it just with a constant, you end up with minus p minus rho g z minus a half rho v squared is equal to 0 plus a constant. I guess it'd be plus a constant on this side, but you don't care what the constant is, so it's just a magnitude that's there. And so that is our expression that we have. Well, you recognize that, right? And so I usually think of this much more conveniently in terms of a length. All these terms should be in pressures. This is certainly a pressure. Rho GZ is unit weight times elevation. That's a pressure as well. And you could work through the units and show that that's the case here, if you so wish. I usually divide this through by the unit weight of fluid, which is rho G. And I always think of Bernoulli's expression as, these are all negative, so pressure plus divided by unit weight of the fluid plus elevation plus velocity squared over 2 times gravity equals constant. So actually we've used nothing other than the things that we had before, right? It's exactly the same expression that we had to be able to define what the fluid pressure is within a static fluid. It happens that the fluid that we're taking, we are moving from this location to this location. It might accelerate as it goes from one place to another. So it has a particular velocity, V1 at this point, pressure 1 at this point, and elevation 1 at this point. And at this other point, it has a velocity which may be different, a pressure which may be different, and obviously in this case, certainly an elevation which is different because they're separated by some physical elevation. And so that's basically how we get Bernoulli's expression to be able to represent our behavior for our system. And so the two expressions that are going to be important in this part of the class, you can think of these as negatives or you can make them positives. It doesn't really matter. Perhaps easier to think of them as positives, are Bernoulli's expression in this differential form and integrated out into a final expression, which is perhaps the way that I'm sure many of you have seen this before and come to know and love it, of course, and to use it as well, right? So that's basically where it comes from. So it's no more different from us being able to evaluate the behavior of fluid within a container as you accelerate it from one point to another. So nothing more than that. So that's it. And so now what we hope to be able to do is to be able to use this expression because, what we want to be able to do, and I'll just draw it back out again. Everyone okay with that? Okay. What we want to be able to do is to be able to look at how things change as you go along a flow line. And so the idea is, if everywhere along this flow line, this magnitude is a constant, if you're able to write this at a couple of different places, the whole issue is this. If you can write it at location 1 and location 2, it's often useful to use location 1 as the upstream and location 2 as the downstream. It doesn't matter at all when we're dealing with inviscid fluids, but when we're talking about viscous fluids where there are physical losses, then it does matter that you write it in that convention. And it also matters that our coordinate system is now, this is the z direction, and we're interested in writing this not in a particular x direction, but we're interested in writing it along a streamline. It happens in this case that the streamline is kind of in the x direction, but all that matters is it physically has to be in the same streamline. So the particles of fluid that go through this point have to ultimately pass through this point sometime later, and then ultimately pass through here as the definition of a streamline. And if that's the case, then we can just write Bernoulli's expression between these two different locations. And just by writing it upstream and writing it downstream. And so we have 6 unknowns in this, and we hope that we can write it so that we have 5 of them known and only 1 of them unknown. That's basically our interest. And so in this particular case, well, I guess you could do it with, let's do it with a slightly different example. So it could be on the wing, which you'd be interested in, but it could also be our jet engine, and you say I have no sense of you. Come on. So this is a streamline going around here. And so this is the so this has to be a streamline. I haven't drawn it as a streamline, but assume this is on a streamline. This is point 1. This is point 2. Make some assumptions here. Let's figure out what's going on. So what do we know here? We want to know what the force is that's applied on here. So we'd like to know what the fluid pressure is at point 2. So we have a streamline velocity at point 1. We have a fluid pressure at point 1. And we have a elevation at point 1. If these are basically at the same height, which they are, right? This is our z-coordinate system. Then take it equal to 0, right? All that matters is it was San Francisco Airport, so it's 10 feet above the water. So it's 3 meters, and it's 3 meters. That's all that matters. All that matters is they equal each other, and so clearly, as you look at this expression, they'll cancel each other out. Whoops, fluid pressure. Well, if you look at the fluid pressure here, it's in the atmosphere. You're feeling atmospheric pressure around it, and so the fluid pressure has to equal atmospheric. And if we're going to use gauge pressures, then that's equal to 0. The pressure here, we don't know. The velocity here, what's the velocity when it comes out of the jet engine? Don't know what that is, but I imagine that you could imagine that if you want to drive an airplane at the speed it flies at, then the velocity of the air coming out of the engine has to be equal to the speed that you're flying, right? You can't imagine going faster than the speed that air is coming out of the back of the engine, just intuitively. And so you could imagine that if a plane can fly at 500 miles an hour, which is roughly the speed I think they fly at, then a maximum, an upper limit on this might be of that order. How much is 500 miles an hour in meters per second? Just so we know. Yes? Will that work? Oh, that's good. 200, it says. Order of 200. So this is something of the order of 200 meters a second. And so what's the velocity here? I didn't draw this very well, but you could imagine that this, if this is the side of the truck, this is the streamline. This is a stagnation point. And so physically, it's the same as me taking this ball and throwing it. I can't do it against this wall because it'll bang into you, into the audience. Throwing this against the wall, it physically gets stopped by the wall, right? It stops, so its velocity is 0. So you're taking the momentum it has, mass times velocity, and the velocity is not just a scalar, it's actually a vector. And so it's changing its direction because it's coming back at me from the bounce. Here, you could imagine that this has to be continuity as you go from here, right? This is a velocity here. Along the streamline, it goes around a corner. But here, the velocity you can take just by convention as equal to 0. It's a stagnation point. You're killing it, right, against the wall of the truck. So if this velocity is equal to 0, then you can fill in what we have that we know here and what we don't know. So the pressure here is atmospheric. This is 0. Z1 and Z2 cancel out, so we don't have to worry about those. We know this velocity here is equal to 200 meters a second. We know that gravity is roughly 10 meters per second squared, 9.81. We'd like to know what this is, and we know that this is 0. Velocity is 0.
I have a question.
Yes.
Why is P1 0 again?
Because it's physically, you have this stream of air here. If you go along to the side of that stream of air, it's the atmosphere, which we're living in. And so it feels that. And so you can imagine that since the fluid pressure acting on the side of that stream of air, like on this pencil, has to be atmospheric. And we know that at a point, fluid pressures in all directions have to be the same, then by definition it's atmospheric. Good enough? Do you understand what I'm saying? So, let me draw it. So you have a stream of air which is coming out like this. We know that the fluid pressure out here in the atmosphere is atmospheric, which is acting all directions. If you take that right onto this thing here, and you look at the fluid pressure acting on this side here, it means the fluid pressure acting normal to this boundary is atmospheric. If you go inside here, then the fluid acting radially into this is also atmospheric. And since we know that the fluid pressure acts the same in all orthogonal directions at a point, albeit for a static fluid, then the pressure here is equal to atmospheric, and we're taking atmospheric as equal to 0 gauge. Okay? Right. And so I think if you looked, so it's a choice. If you looked inside this engine here, where it's confined, almost certainly it wouldn't be atmospheric, right? Because it's expanding and it's constrained, and that's why it's shooting out the back. But so you have to choose where you might want to take it. And so if you took it inside here at point P0, I think it would not be equal to P atmospheric. In fact, you could make a good case that it'd be much larger than that, right? Because it's getting squeezed out. But once it comes into the atmosphere, it has to be acting at atmospheric pressure. And so if you wanted to, then, so just by rearranging this, what are we left with? We're left with basically the fluid pressure applied on the truck is equal to the unit weight of fluid times velocity 1 squared divided by 2g, which is the same as rho g v1 squared over 2g. Let's get rid of these. Which is just equal to the density. Density of air is about 1 kilogram per meter cubed, something of that order. Velocity 1 squared is going to be 4 times 10 to the 4 meters squared second squared, right? So 200 squared should be 2 squared times 100 squared and divided by 2, which gives a number which is 2 times 10 to the 4 kilograms meter cubed meter squared second squared. And does that make sense? Density, velocity. So in other words, what's a Newton? 1 Newton equals 1 kilogram meter per second squared. Kilogram kilograms, yes, this is, say it again, sorry? Yeah, so it should be newtons per meter squared, right? So, and so, yes, okay. So in other words, this is kilograms, yeah, right. So 2 times 10 to the 4, so it should be pressure. It should be kilogram meters per second squared. Kilograms meters per second squared over meters squared, right? So we're left with meters over meters cubed, which is 1 over meter squared. So it's the right units, so you can check the units. So the force, the pressure that's applied is this. If you multiply the pressure by the area to a rough magnitude, you get a magnitude of the size of the force that you're applying to the truck. And obviously the size of the force that's applied to the truck, so pressure times area equals force. And if you know what the force is, and you know what the mass of the truck is, you could figure out what the acceleration is traveling. So, relatively straightforward calculation, but one that comes out of just an application of applying Bernoulli. So, the interesting thing, I think, out of this is that it comes really out of the expressions that we've used already for a static fluid. And just by writing it at two different locations and along a streamline. So that's the key issue. So the key issues here, I think, as you look back on this, is that when we use Bernoulli expression, you have to kind of be selective about how you choose your locations. I think the point that was made here about the jet engine and the pressure choices, if you choose your pressure here, then, and you try to work out your solution, then in this particular location, if we chose to use this point rather than this point, is that, and this is the truck, and this is P2, elevation 2, and velocity 2. So you need to be careful. You could write your equations at any point along this, right? You could choose this point, but you want to choose it where you actually know enough about your conditions to be able to resolve your 6 expressions, and you need to know 5 unknowns to solve for the remaining unknown. 5 knowns for the remaining unknown. If you wrote it inside the jet engine, you'd certainly know the elevation, because it's roughly the same as the others. It would probably be the same velocity as V1, because it's coming out at some from continuity. But what you wouldn't know here was you wouldn't know your fluid pressure, because you don't. And so if you wanted to be able to define what the fluid pressure is here, in writing this you'd have 6 expressions, but you'd have 2 unknowns and you couldn't solve it. If you choose to write it just outside here, for the rationale we gave here, that as soon as it enters into the air, as soon as it comes around this lip, roughly, it won't be exactly, but roughly it should be equal to the atmospheric fluid pressure, because fluid pressures at a point act in the same, are equal in all directions, and they have to be atmospheric pressure outside this stream. So as you go normal to this stream, you can make an argument that it should also be atmospheric pressure inside this stream. You know this, you know the elevation, and you can estimate the velocity. If you know the elevation and you know that you've killed all the momentum of this stream, just like this ball hitting the wall and the velocity going to 0 as it hits the wall, mass times velocity, you've killed the momentum. That's exactly what we're doing here, is that as this goes to 0 at the stagnation point, then we're left with only one unknown to be able to determine. And that's really all we need to know about Bernoulli. The expressions we have, remember, we've only used it in one form so far, but the expression comes in 2 different forms. One, if you like, not quite ready for use, and one ready for use. We'll use the not quite ready for use in some cases because it allows you to accommodate the fact that, for instance, you might have a density of a gas which isn't constant in space. But we'll leave that for another time. Okay, I think that's it for today.